Okay, Assalamu alaikum jami'an. And welcome to our 10th lecture on this series on selected topics on radiation physics. We have covered so far interactions of photons in matter, interactions of charged particles in matter. And now we're going to start to introduce a new topic, which is cavity theory. So let's share. Is the presentation visible to all of you?
واضح.
Visible to me.
Okay. So cavity theory. So what is cavity theory? So usually in radiation dosimetry, we want to measure a dose in medium, for example, in phantom, in water, but we will use actually a detector to conduct this measurement. It's difficult, except I think for calorimetry, to measure the dose directly in a medium. So in calorimetry, we actually measure change in heat, and based on that, using the specific heat for water, we can directly measure the dose in water. However, when other dosimeters are used, usually we measure the dose in the dosimeter, and then we need somehow to calculate or to predict what would be the dose in the medium when the dosimeter is not present. So this is our interest is to measure the dose in medium when the this measuring detector is not present. This is graphically shown by this diagram. We have a dosimeter, and usually we're going to measure the dose inside this dosimeter, and this dosimeter is made out of a material different than our medium of interest. So the medium of interest is surrounding the dosimeter. So suppose we were able to determine what is the dose in this dosimeter or in this cavity. So remember, when we say cavity, we mean there is a material surrounded by a medium of interest. We are not interested in knowing the dose inside this dosimeter, but we are interested to know the dose in the medium when this dosimeter is not present or when this cavity is not present. So the way to do this, the way to relate the dose of the medium, the dose in the cavity, we're calling it here D sub G. So that's dose in gas, usually because the dosimeter, usually they are gas material or air specifically. But this is the general representation, the dose in the gas and the dose in the medium. When the dosimeter is, or when the cavity is not present, they are related by a cavity theory. So there are three categories or three situations of cavity theories. We have a small cavity theory, we have a large cavity theory, and then we have a cavity theory. It's an integrated cavity theory, or sometimes it's called general cavity theory or Berlin cavity theory. Furthermore, the small cavity theory, we have two theories that are subcategories of small cavity theories. One is the famous Bragg-Gray cavity theory, and the other one is the Spencer-Attix cavity theory. So remember, the Bragg-Gray and the Spencer-Attix, they are part of or subcategories of small cavity theories. Of a small cavity theory, we have a large cavity theory, and then we have a general cavity theory, or as an intermediate cavity theory. So the Bragg-Gray cavity theory, basically, when we have this, when we have our cavity inside the medium, In order to apply the Bragg-Gray cavity theory, two conditions need to be met. So the first condition is that the dimensions of the cavity the cavity is small, should be small with respect to the range of charged particles. So we have charged particles coming from the medium, the surrounding medium, and entering or crossing this cavity. If the charged particle range is actually larger than the cavity dimensions, then this is satisfies the first condition of the Bragg-Gray cavity theory. The other condition is that this cavity does not perturb the charged particle field, meaning that if these charged particles entering the cavity, they would have, for example, a fluence. They will have a certain energy, directions, and so on. So when we remove the cavity, the same particle fluence, the same charged particle fluence should also be present in the medium at that point of interest. So when these two conditions are met, then we say that these conditions or the situation could be described by the small cavity theory, or more particularly on the Bragg-Gray cavity theory. So based on this, the absorbed dose in the cavity is actually deposited by charged particles coming from outside the cavity. No charged particle is created inside the cavity, except, of course, the secondary electrons. But for example, if we have a photon beam and the photon is interacting in the medium, in order and when they interact in the medium, they are actually going to create electrons. So the dose in the cavity is essentially going to be deposited by these electrons generated in the surrounding medium. No photons interact in the cavity and produce electrons with the cavity. This is depicted here. This is the first condition where now the dose in the cavity is actually deposited by charged particles that are crossing the cavity. These charged particles are coming from the surrounding medium. And these charged particles, their range should be larger than the dimensions of the cavity. So that's the first condition. The second condition is that, okay, we have a fluence of charged particles crossing the cavity. Now, when we remove the cavity, well, the fluence would remain the same, or at least at that point of interest. So nothing has been changed. The cavity does not change anything on the number of charged particles, on their directions, or on their energy. So when these two conditions are met, then we can apply the Bragg-Gray cavity theory. And the Bragg-Gray cavity theory states that the dose in the medium divided by the dose in the cavity is given by the ratio of the collisional mass stopping powers of medium to that for the cavity. So in notation, I think you're familiar with this notation. It's the mass collision power medium to gas. So what we need to do, we need to look up, for example, what's the fluence or the fluence of the charged particles crossing the cavity, and then we go and look up tables to get the mean stopping powers for the medium and the mean stopping powers for the cavity inside the cavity material, and these are how the doses are related with this equation. Thus, if we had a way to determine the dose in the cavity, so imagine this cavity is a detector, a dosimeter, if we manage to actually determine the dose inside that dosimeter, then the dose in medium will be just the product of the dose in the dosimeter multiplied by the ratio of the collisional stopping powers, medium to gas, or gas material, cavity material. So the Spencer-Attix cavity theory is the second small cavity theory. And in Bragg-Gray cavity theory, there is a problem. The problem is that as the charged particle crosses the cavity, it is going to interact inside the cavity and will produce secondary electrons. It could happen that some of these electrons might gain high energy, and they will leave the cavity. So we're talking about the electrons, the secondary electrons produced in the cavity by the primary charged particles. They may gain sufficient energy to leave the cavity. Thus, the dose or the energy that was given to them, part of it will actually be deposited outside of the cavity. So, in a sense, the Bragg-Gray cavity theory overestimates the dose deposited in the cavity. Here is the situation is depicted by this. So we have the charged particles. The charged particles, they have their range is larger than the cavity, the dimensions of the cavity. But as they enter the cavity, they're going to interact through collision interactions, and they will transfer energy to orbital electrons of the medium inside the cavity. And some of these orbital electrons will gain sufficient energy such that they are capable of actually keeping the cavity. Okay? So these usually we call these electrons delta rays. So Spencer-Attix, they came up with a solution to this issue, or let's say it's an extension to the Bragg-Gray cavity theory in an approximate manner. So basically what they say, all the electrons above this cutoff energy, we're going to select a cutoff energy. So for example, 10 keV, 100 keV, it will depend on the problem in hand, will depend also on the size of our dosimeter. So these are now considered to be part of the fluence spectrum. What does this mean? It means that these electrons produced with higher energies higher than delta, then basically we're going to retake them, add them to the fluence that is entering into the cavity. So all energy losses below delta, so if the secondary electrons have energy below this delta, the assumption is that these electrons, they're not going to go outside of the cavity, and thus they will deposit their dose locally inside the cavity. However, for those electrons, secondary electrons with energy above delta, those are going to escape the cavity. They will not deposit the dose in the cavity, but they are present. So the idea is that these electrons, then these delta rays, we're going to reconsider them as part of the fluence that is entering the cavity. So the local energy loss, we can calculate this using the restricted collisional stopping power. And as we talked about this last time, the restricted collisional stopping power is basically all the energy that is transferred to secondary electrons below a cutoff energy of delta. So the Spencer-Attix cavity theory then states that the dose in the medium equals to the dose in the cavity multiplied by the mean restricted collisional stopping powers of the medium to the gas. So this is the difference. In the Bragg-Gray cavity theory, this was the unrestricted collisional stopping power. That means all secondary electrons, regardless of their energies, The assumption is that these secondary electrons, they will not escape the cavity and deposit those locally. However, Spencer-Attix cavity theory states that in order to get the dose more accurately, one needs to use the restricted collision stopping power of the medium to that of the gas. And as I mentioned, this delta, this cutoff energy, this will depend on the problem in hand, depend on the size of our dosimeter. Note that for the Spencer-Attix cavity theory to be applicable, still the two conditions for the Bragg-Gray cavity theory needs to be met. Namely, the range of the charged particle, this is the primary fluence, it still needs to be greater than, a lot of typos in my slides, I'll correct them. They need to be greater than the cavity dimensions. And the other condition is that the cavity, the presence of the cavity does not perturb the fluence, meaning that the fluence, when the cavity is removed, will be the same, will not be changed. So the cavity does not perturb the fluence, the charged particles. Now we go to the other extreme. So the small cavity theory, remember, no charged particles are created in the cavity except the secondary electrons. And the dose deposited in the cavity is actually produced by charged particles produced in the medium or coming from the surrounding medium. Now, the large cavity theory is completely the opposite extreme. Basically, the dose in the cavity is now deposited by electrons generated in the cavity material. So if we have charged particles produced outside of the cavity, the assumption is that these charged particles, particles will deposit their dose locally. They will not have sufficient energy to enter inside the cavity, and then the dose in the cavity will be produced by charged particles created in the cavity. So essentially, this large cavity theory, this applies to photons, because we can have a photon that is, it can actually avoid interaction in a medium, but then it will interact in the cavity. It will generate electrons, transfer energy to electrons within the cavity. So if a photon, essentially, if a photon interacts outside of the cavity and produces or transfer energy to this electron, the assumption is that the energy of this electron is very low, such that it will deposit its dose locally at the point of interaction. So the electrons generated in the surrounding medium deposit the dose locally. Hence, they do not contribute to the dose in the cavity. Essentially, the presence of the cavity in the medium, and also the other condition is that we need to have that the presence in the cavity in the medium does not perturb the fluence. Remember, our goal is to determine the dose in medium when this cavity is removed. So if the fluence, essentially, it needs to be the same. So when these two conditions are met, then the large cavity theory, or let's look at this, it's a depiction of what's happening. So we have photons. These photons, some of these photons will interact in the medium, will generate secondary electrons. Some of the photons just go through the medium, and some of the photons will actually interact within the cavity. So the dose in the cavity is deposited by the secondary electrons produced by the photons. These are the yellow electrons here. Okay, these are secondary electrons produced in the cavity. Whereas these red electrons, these are the secondary electrons produced in the surrounding medium. And the assumption in the large cavity theory is that these electrons, they do not contribute to the dose in the cavity. Okay, essentially, in the large cavity theory, the medium does not exist. So if we look at the dose in the cavity, the dose coming from photons interacting with the cavity in the large cavity theory. Essentially, the surrounding medium does not exist. The dose is blind to that. It does not see that. It does not. So that's essentially what this means. So if this condition of the large cavity theory are met, the two conditions, remember that the dose is deposited from electrons generated within the cavity and no electrons from the medium contribute to the dose in the cavity. And the second condition is that the cavity, the presence of the cavity does not perturb the fluence. So the fluence remains the same when the cavity is removed. So if these two conditions are met, then the dose in medium is equal to the dose to the cavity multiplied by the mass energy absorption coefficient, the ratio of the mass energy absorption coefficient. Of course, here we take an average because we're averaging over the total photon fluence that is depositing the dose in the cavity. So as you mentioned, we have a small cavity theory, we have a large cavity theory, and both these theories, they represent actually two extreme situations. The small cavity theory, the dose is deposited by electrons generated in the surrounding medium. In large cavity theory, the dose is deposited by electrons generated within the cavity.
Sir, excuse me, can I interrupt you?
Yes.
So in the large cavity theory, we're saying that the electrons are being generated inside the cavity itself. So by this way, I think the cavity is perturbing the beam.
No. Well,
So,
look, when we say
so,
the cavity is perturbing or not perturbing, this will depend on the dimension. I mean, suppose that the fluence, the cavity is not does not perturb the beam. Then we're meeting the condition. No cavity theory is perfect. Okay, so even in the small cavity theory, when we say that, like, okay, the cavity, the presence of the cavity does not perturb the fluence, this is not true. Because now electrons, when the way they interact their path in the cavity is different than their paths in the medium. So definitely the presence of the cavity perturbs the fluence, even in small cavity theory. But what we're talking about in an ideal situation. So if the presence of the cavity does not perturb, then we can apply the small cavity theory or the large cavity theory. Okay.
yes, exactly. So as the definition mentioned in the small cavity theory, I understood that perturbing the beam means that the photons does not interact inside the cavity. Am I right?
No. That is the first condition. The first condition is that the photons do not interact. That means that the dose in the cavity is actually produced by electrons generated from the surrounding medium. So photons are going to interact in the surrounding medium. They're going to, so we're talking about a photon beam, by the way. But it could be, for example, a charged particle. But anyway, if we have a photon beam, and suppose the small cavity conditions apply, what does this mean? It means that the photons only interact with the surrounding medium. The photon beam does not see the cavity. It's not going to interact in the cavity, and it does not see the cavity. And the dose deposited in the cavity, this will be due to the electrons produced from the surrounding. Okay, This is a situation for a charge, I mean, it's charged particle, but imagine if we had photons, if we add to this figure, okay, or this figure, imagine if we had photons. The photons, basically, they are producing these electrons, okay? They interact in the medium, and they are producing these electrons. These electrons, these are the ones that are going to be responsible for depositing the dose in the cavity. The photons will not interact in the cavity. They will not produce charged particles or electrons within the cavity. Okay, so the dose in the cavity is essentially produced by the charged particles created outside of the cavity. The photons, they do not see the cavity. The cavity does not exist for the photons. That's the idea. Okay. When this situation happens, and provided that the charged particles, they have a large range that they can cross the cavity, then we can apply the small cavity theories, whether it's the Bragg-Gray or the Spencer-Attix. But now we're looking at the other extreme. So in the other extreme is that photons, essentially, they can interact with the surrounding medium, and they can interact with the cavity. But the dose in the cavity in this situation is only deposited by these electrons that are generated from photons interacting in the cavity. Electrons produced outside of the cavity, they do not actually enter the cavity. They do not deposit those there. And this will apply, for example, if we have a low energy photon beam, where the energy transfer to the electrons is very small, and these electrons, they will, once they're generated, they will, their range is very, very small. They cannot actually enter the cavity. Okay? So that is the assumption, how the dose, or what's the source of the dose in the small cavity, or in the cavity, or the large cavity theory. Now, the problem is now, if we want to look at when we have, okay, I don't have a figure for it, but now, remember, what we're interested in, we're not interested in the dose in the cavity. We're interested in the dose in the medium. So if we remove this cavity and put medium there, then we are interested in the dose in the medium there. So if the cavity fluence, or the cavity does not perturb the fluence, meaning that if the fluence of photons at that point of interest is equal to the fluence of photons within the cavity, then we can apply the large cavity theory. We know this is not true. I mean, I agree with you. But if this was true, then we can apply the large cavity theory. And the large cavity theory states that the dose in the medium is given by the dose in the gas multiplied by the mass energy, the ratio of the mass energy absorption coefficients for the medium and the gas. Okay?
Yeah, so I just misunderstood the definition of perturbance. So ideally, the photons should not, I mean, no photons should be generated, for example, by the walls of the cavity. This is the ideal case.
I did not talk about a wall. Now, I don't know if we're getting a wall.
I mean, just an example. I mean, no photons are being generated by the cavity itself. No new photons, right? Just the fluence passing through the cavity is just equal to the fluence of the photons passing the medium outside the cavity. Am I right?
Say that again.
So, what I'm understanding from the perturbance is that no new photons are being generated inside the cavity, so that the number of photons passing through the medium outside the cavity is exactly the same as the number of photons passing the cavity. Am I right?
Well, it's the photon. Okay, when we remove the cavity and we have this point of interest in medium, we want the same photon fluence entering this point of interest in the medium to be equal to the same fluence of the photons entering the cavity.
Yeah, okay, thank you.
Yeah. So if these conditions are met for the large cavity theory, then the dose to medium equals to the dose to the dose within the cavity multiplied by the mass energy absorption coefficient. Okay, I think if you look at Han or Americans, they like to use the subscript of En, but Jones and Cunningham use it as subscript of AB. I like to use AB because it's clearer, because we have energy transfer and energy absorbed. So, so the intermediate cavity theory now support in reality. So the small cavity theories, they represent two extremes. And in reality, when we measure doses for a photon beam, many of these cavities or detectors, they do not fall into a pure small or a pure large cavity. So in such scenarios, we don't really have an exact theory. So we don't have, okay, we can use stopping powers or blah, blah. We don't have this. But we can use a general cavity theory as an approximation. Okay, this general cavity theory sometimes is called an intermediate cavity theory, or it's called the Berlin cavity theory. It's known for with these names. And basically, it's very simple. So we can think of it as it's a weighted combination of the small and large cavity theories. So if we have a cavity, and suppose we know the dose in the cavity, and we know, for example, the fraction of the dose that was deposited by electrons generated within the cavity, and the fraction of the dose generated or deposited by electrons from the surrounding medium. If we know these two weights, then okay, then we can actually make use of the small and cavity theories in order to determine the dose within the cavity. Okay, so the situation, we have a cavity, we have photons, and then with the photons, so we get secondary electrons that are generated within the cavity by these photons, or we have secondary electrons generated by photons interacting in the medium. So for these red photons, okay, we can apply the small cavity theory. And for these for these red electrons, we can apply the small cavity theory. And for these electrons, we can apply the large cavity theory. So the only issue is we need to know the weights of the dose from the red electrons and the dose from the yellow electrons. So if we know this fraction, if this fraction is F, then we can combine the dose or get the dose in the medium as a combination of these two cavity theories. So if F represents the fraction of the cavity dose from electrons from the surrounding medium, essentially, this is the dose by the red electrons, then 1 minus F would be the dose from the yellow electrons. Okay, so this is the fraction of the total dose. So for these, for the red electrons, the ones that are generated from the surrounding medium, we can use the small cavity theory. And then for the remaining dose, which was actually deposited by electrons produced within the cavity, we can use the large cavity theory. Okay, so essentially this is the problem is, okay, what is F? If we know F, F probably could be, I think through Monte Carlo simulations, so on, we could actually get an estimate of F. And obviously, F will depend on the beam, on the energies, and on the cavity size and medium. Okay, so this is the intermediate or the general cavity theory. So now let's come to this problem, like what Ali was talking about. Now he talked about the wall. So now we want to introduce a wall, because this is obviously ionization chambers that we use, typically used to measure doses. They consist of a cavity inside, which is air-filled. So this is a gas material. And they will also consist of a wall material that is usually made out of graphite. But again, what is our interest? Our interest is to determine the dose when this chamber is not in the medium, neither the cavity nor the wall. That's our interest. Okay. So again, this is depicted here. We have a wall, we have a gas, okay, or air in this case, and we know the dose in the air. Okay, we know the dose in the air, and all of this, the chamber is surrounded by a medium M, let's say water. We are interested to know the dose in phantom when this chamber and wall is not present. So let's look at the situation now. So we have photon beams. Okay, we have a photon, and this photon can interact with the medium. It can interact with the wall, and it can interact with the cavity, okay, or with it. So essentially, we have actually the dose deposit in the cavity. Essentially, it's coming from three sources of electrons. Now here I'm talking about high energy electrons, okay? High energy photons. So they can transfer significant energy to electrons. We have electrons, we have those coming or deposited by the red electrons, which were produced in the surrounding medium. We have those in the cavity deposited by electrons generated from the cavity, from the chamber wall. Those are in yellow. And then we have here, this is in orange, we have a few electrons or a dose deposited by photons interacting within the cavity. Okay, so we have three sources. This is the real situation. Okay. We can make some assumptions. The first assumption is that, okay, this is air, and density of air is 1/1000, the density of water and the density of the wall material. So the first assumption we're going to make is that, okay, photons or the dose actually deposited by photons interacting, or the number of photons interacting with the cavity is negligible compared to the photons interacting in the surrounding medium or in the wall. And this is due to the density. Okay, the density is very, very low. So essentially, we can then approximate the dose in the cavity to be produced or to be deposited by two sources, not three sources. And these sources will be electrons generated from the medium. So photons interacting with the medium generating these electrons. And then also by electrons generated within the wall material. So if the wall is not present, this should be a small cavity theory, right? So if we don't have, if the wall is too thin or very thin or it's not present, then we should get back our small cavity theory. So Spencer-Attix, whether Spencer-Attix or Bragg-Gray. Okay, so these are the two sources of the dose deposit in the cavity. So let's look at both types of electrons or from the sources. So we have these red electrons For these red electrons, okay, the wall is not present. They are generated outside. And as they penetrate or they go through the cavity, they will deposit those inside the cavity here, okay, generating secondary electrons and so on. So we can use for these electrons, we can use the Spencer-Attix because this mimics a small cavity theory. So the dose for these electrons is just going to be the fraction of the dose in the cavity produced by these electrons multiplied by the ratio of restricted collision or stopping power medium to gas. So here I'm putting 1 minus alpha because that's the conventional way. They use alpha. Alpha represents the fraction of, you look here, alpha represents the fraction of the dose in the cavity deposited by electrons generated in the wall. So essentially, when the wall is thin, alpha is going to equal to 0 in this situation, okay? So when alpha is 0, okay, alpha is 0, then you see we get back our small cavity theory. Alpha is 0, then we get the dose in the medium equals to the dose in the gas multiplied by the ratio of the restricted collision stopping power medium to gas. So this, if we use this for these electrons, then we can calculate what would be the dose in the medium when the cavity is not present. And we're going to call that D medium 1 because that's the first source, okay? So D medium 1 equals to 1 minus alpha multiplied by the dose in the gas multiplied by the ratio of the restricted collision stopping power. So for these electrons, the wall appears, it's not there, it's absent. It doesn't see them. Or the cavity thinks that these electrons coming from the medium as if the wall is not present. So this is just the cavity theory. So we have the dose in the cavity from these electrons. It's just given by the Spencer or small cavity theory. We'll select the Spencer-Attix cavity theory. And this will give me the dose in medium from these that source of electrons. How about the other situation, or for the other electrons? Photons, they are now interacting in the, or some of the photons will interact with the wall, and they will produce electrons. So for this, I mean, now we get a dose in the cavity from these electrons generated in the wall. So essentially, that part of the dose, the wall material acts as the surrounding medium. Okay? So for these electrons, we can then use the Spencer-Attix cavity theory to calculate what is the dose in the wall. Essentially, what we're doing is that, okay, let's look at this figure. I like this one better. But this is the situation we have. These electrons are produced in the wall, and they deposit those in the cavity. Okay, so we can, the surrounding medium in this situation for the cavity is going to be the wall because that's the source of the electrons. So what we can do, we can replace this cavity now with wall. So it comes like this. I left the same dimension, but actually the wall size, or it's going to be small, but I left it the same dimensions. Essentially, the dose in the cavity from these electrons, the cavity does not see the phantom, thinks that the phantom is not present, because that part of the dose It was generated by electrons from the wall. Okay. So this is what we end up with. We have now, using the small cavity theory, Spencer-Attix, for these electrons generated in the wall, we're getting this situation. We're getting the dose now in the wall, okay, surrounded by the medium. But remember, our interest is to get the dose in the medium. We are not interested in getting the dose in the wall. So now in this situation, the dose in the wall was deposited by electrons generated within the wall. So the dose in the wall was not actually deposited by electrons from the medium. It was deposited by electrons generated within the wall. And this reminds us by the large cavity theory now. So now what we can do, we can then remove the wall, replace it with medium, and then relate the two doses, medium and wall, by the large cavity theory. Okay, so in this situation, the dose in the medium now, because that's our ultimate interest. So the second source, remember, these are electrons generated from the wall, is given by the dose in the wall multiplied by the ratio of the mass energy absorption coefficients, medium to wall. It's not cavity, medium to wall. But we know the dose in the wall. The dose in the wall is just equals to the dose in the cavity multiplied by alpha, because that's the fraction of the dose in the cavity deposited by these electrons multiplied by the Spencer-Attix cavity theory. Okay, so this part here is basically this. So remember, this is how the dose, how we calculated the dose in the wall, equals to dose to the cavity or dose to the gas from these electrons. That's why we have an alpha multiplied by the mass energy restricted collision of stopping powers, wall to gas. So we ended up the dose from these electrons generated in the wall is given by this relationship. It's the fraction of the dose in the cavity from that from electrons produced in the wall multiplied by the restricted collision of stopping powers, wall to gas, multiplied by the mass energy absorption coefficients of medium to wall. See, it's wall here. Okay, clear so far? So this is what we're having. We're having electrons produced in the wall, giving us the dose in the wall and the dose in the medium. When we remove the wall, then it's given by the ratio of the mass energy absorption coefficient of medium to wall. Okay. So now we want to combine the dose from both sources of electrons. We want the dose from the electrons generated from the medium and depositing those to the cavity. These are the red electrons, as well as we want the dose to the medium from electrons generated or produced in the wall. Okay, so all what we do is just we sum the two doses here. So that's the total dose in the medium when the chamber with its wall is not present in the medium. And this is given by the first part is just the fraction of the dose from the red electrons. Those are electrons generated from the medium multiplied by the mass, the restricted collision or stopping power of the medium to gas, plus the fraction of the dose for electrons generated within the wall, and it's given by the product of that dose fraction multiplied by the restricted collision or stopping power of gas, wall to gas. See here, it's medium to gas. Here it is wall to gas. Multiplied by the mass energy absorption coefficient of mass to wall. Okay, so it's just for those electrons, it's like a two-step. From the cavity, we calculate what's the dose in the wall when the cavity, or basically we're replacing the cavity by wall material, calculating the dose in the wall, and then we are removing the wall using the large, some large cavity theory to calculate the dose in the medium when the wall is not present. So this is, we can write this equation neatly. This is the dose in the medium equals to dose to gas multiplied by this part here. Okay. And there are some data of, this is here is for cobalt. We have some data for this fraction, the fraction of the dose produced or deposited by electrons produced in the wall. So as alpha, or as the wall thickness increases, then alpha will become 1, and then 1 minus alpha will be 0. Essentially, that the full dose in the cavity is then produced by electrons interacting or produced from the wall. That's when we have a thick wall. The other opposite scenario is when the wall is very thin. When the wall is very thin, this fraction is going to go to 0. And as this fraction alpha goes to 0, what happens? This part is going to be 0. And here we are left by the Spencer-Attix cavity theory alone. So if we have a very thin wall, alpha equals to 0, then the dose is given by, so for very thin wall, alpha is equal to 0, and the dose is then given by the Spencer-Attix cavity theory alone. So we retain back our Spencer-Attix cavity theory. This is another figure. So that alpha, that fraction, depends also on the energy of the beam. Okay, so this is a photon. It's a pure, it's a photon thing, right? Because it talks about production of the charged particles. So if you have an electron beam, doesn't matter. But if you have photons, then the photons, when they interact, they produce the charged particles. So it's important to know from where these charged particles were produced. Here, this is actually from TG21. I don't know if you have actually applied that protocol to calibrate linear accelerators or not. It's a lengthy protocol, but basically for a given nominal accelerating potential, this alpha will depend on the thickness of the wall. The thicker the wall, then the higher is the value of alpha. Cobalt is probably less than here. Okay, that's 1.25. It's somewhere less than that. Cobalt specifically is this figure. But this is a more generalized figure for nominal other energies, or the other photon beam energies. So what we see is so if we have the same wall thickness, as we increase the photon energy, what's happening? The fraction of the dose deposited in the cavity by the wall actually decreases. Because the attenuation, think of the attenuation. What happens if we have the same wall thickness? The attenuation in the wall decreases. That means that the fraction of electrons or the number of photons interacting in the wall compared to the number of photons interacting in the surrounding medium is going to decrease. And again, as the wall thickness increases, if we fixed beam energy, we see that its alpha is going to increase. The thicker the wall, the more dose. The more dose is actually going to be deposited by, or the fraction of the dose is going to increase of those electrons produced within the wall material. So usually, I don't know if you have seen an equation like this before or not, but usually we like to write this equation in a very neat way, in a very nice way. So we like to write it as the product of the dose multiplied by restricted collision stopping power. Essentially, this part is a pure Spencer-Attix cavity theory multiplied by a perturbation factor. So what we do is we factorize, we take out this part here, the restricted collision or stopping power, medium to gas. We take it as a common factor and put it here with the dose. So we end up with 1 minus alpha, this part, and then we have the alpha. And here we need to, because these are ratios, then we need to change this ratio. If you do that, then this transforms into the restricted collision or stopping power of wall to medium, okay? Multiplied by this factor, which is the mass energy absorption coefficient medium to wall. So this part, so what we're seeing now is that this here, the restricted collision stopping power, this is a parameter that depends on the beam energy. It does not depend on the chamber, does not depend on the dimensions of the chamber, or depends on the wall thickness or material. It's not there. Whereas this perturbation factor, P1, it's a factor that depends both on the energy as well as on the thickness and material of the wall. Okay? So I've just took a copy or just part of the TG21, because this is ultimately what we're going to be looking at next time, inshallah. But anyway, the dose equation is given by a restricted collision or stopping power ratio of medium to gas. This is the Spencer-Attix cavity here. Multiplied by, we have here a P1. And in the protocol, they actually give you how to calculate P1. All what we need to know is the energy, and we need to know this alpha, as I showed you the figures, the previous figures for alpha. So once we determine the alpha and the mass energy, the restricted collision stopping powers, and the mass energy, we need this factor, the mass energy absorption coefficient, then we can plug in the data, and this will give me then the P1. Of course, it's written a little bit differently than here. What they have done is just they divided throughout this part by the restricted collision or stopping power and left it in the equation. So essentially, because the protocol will have actually data for the ratio of restricted stopping powers, medium to gas or wall to gas, and this you can find in the protocol. Okay, but essentially this equation and this equation, they're essentially the same. It's just written in a different way. The only difference is this part here, I have wall medium, and here it's this part where they have wall gas, and then when we divide it by medium gas, so the restricted stopping powers for the gas, they will cancel out, and we end up by wall to medium. So probably I'm thinking to stop at this slide because next time, inshallah, we will go further on this topic. So we're going to see, for example, how can we determine the dose in a gas? We're talking about air. So for ionization chambers filled with air, we're going to look at how we can determine the dose in the gas. And then we will further introduce additional correction factors. Because as I mentioned earlier, a chamber that does not perturb the phantom, I don't think this chamber exists. And up to what we have done so far, we assume is that the presence of the chamber or the cavity does not perturb the fluence in the medium, but this is actually not true. So we will need additional correction factors. This is the equation. It's the P walk, the P replacement. This is actually a correction factor to account for the changes of fluence with the chamber and without the chamber. But we're going to look, inshallah, onto this dose equation next time, and we'll define this N-gas calibration coefficient for a chamber. And then once we have done that, then, okay, we're going to look into the more commonly used calibration factor for chambers. This is the NDW that probably all of you are using to calibrate linear accelerators, whether you're using the TRS-398 or you are using the TG51, because these two protocols are based on the NDW. But in the past, we used to do it with the N-gas concept, and it has some really nice or very some advantages. But as you will see, okay, a lot of correction factors that the physicist will need to actually go and grab this data from somewhere. But newer protocol, the NDW based protocol, we only need to take one factor, the K sub Q. And we will actually derive that K sub Q. We will see, we'll understand what does it mean actually more and more. So probably I'm going to stop here today and continue from there. We're going to talk about how to get the dose in the air cavity and then define this N-gas and other perturbation factors and so on. Okay. So any questions? No questions؟ حتى بالعربي يعني مش مشكلة يعني. Was it clear, not clear? I'm gonna stop the recording then.
Yes, sir, it was very clear. I have to admit that this is the first time it has been explained